The objectives of this part are to discuss the first order logic and to understand reasoning in artificial intelligence. What is first order logic? First order logic, also known as predicate logic or predicate calculus, is much more powerful than propositional or Boolean logic. In essence, it has greater expressive power than propositional logic, and it allows for facts, objects, and relations to be incorporated in its statements. In programming terms, it allows classes, functions, and variables to be incorporated in its logic. Advantages of first order logic are: first order logic assumes that the world contains objects, example, people, houses, numbers, theories, colors, football games, wars, centuries, and so on. And it also contains relations, for example, red, round, prime, bogus, multi-storied, brother of, bigger than, inside, part of, has color, occurred after, owns, comes in between, and so on. And it also finally contains functions. Examples can be father of, best friend, third quarter of, one more thing, beginning of, and so on. In this table, we see all the types of logics and their formats. So the first is propositional logic. It contains only facts which are known to be true, false, or unknown. And the next one is first order logic that we are discussing right now. It contains facts plus objects and relations or functions, and propositional statement representing that first order logic can be either true, false, or unknown. Next, we have temporal logic. It is another form of logic in which an additional times factor is included in the ontological commitment, and it can be also either true, false, or unknown. And another one is probability theory. So this theory deals with a degree of belief on facts, and the degree of belief can be element of any value between 0 and 1. So you know probability is always between 0 and 1, and a probability of a fact can be also termed as degree of belief, which is shown on the right side here. I deal with probability theory in later classes again. Finally, we have fuzzy logic. We will also deal with this in later classes. Fuzzy logic in fact deals with an uncertainty or a degree of truth, which can be a value from 0 to 1 again. So the basic statement is itself uncertain, and the degree of the truth of that uncertain statement lies between 0 and 1, and that value is a known interval value that is shown on the right side. That statement's known value is the degree of truth. Next, we see syntax of first order logic. First order logic can contain constants which can be either strings or integers and so on. For example, King John, the number 2, and so on. It can also contain predicates. Predicates are form of statements which can infer that relation between two variables. For example, brother, greater than, and so on. Functions also form the syntax of first order logic. So functions can be an operation on any of the other operators. So it can be, for example, sqrt, that is square root, or left arm of, and so on. Next, we have variables that can be x, y, a, b, and so on, and they represent any of the statements of first order logic. Next, we have the connectives. Major connectives are and, or, not, implies, and if and only if operator, as shown here next to connectives term. Next, we have the equality operator that determines the equality of two statements, and next we have quantifiers, which I will deal with soon. The existential and for all quantifiers are basically implied here. Next, we see components of first order logic. First one component shown here is term. For example, constant, which is a syntax part of first order logic, and it can be, for example, red, or function of constant, example, color of block 1. So block 1 is a constant here and color is a function here. So this is total function of constant. So these all can be a single term. Next we have an atomic sentence. Atomic sentence are predicate relating objects. So no variable is included in these atomic sentences. So this is an object John and this is an object Richard, and this predicate here brother implies that they both are brothers. Similarly, mother of John and father of John are shown to be married here. So basically atomic sentence contains predicate that relate objects. Next we have similarly complex sentences. So instead of atomic sentences we have complex sentences that are conjuncted with logical connectives. For example, John and Richard are brothers, which is shown by the first statement here. This is an atomic statement from here to here. And John and father of John are not brothers. This is another atomic sentence which is shown from here. These both are connected by this logical connective AND. So this is the complete complex sentence from here to here. Next we see quantifiers, which are again a for part of syntax of first order logic. So specifically I have told quantifiers are the universal and the existential quantifier as shown here. So each quantifier defines a variable for the duration of the following expression and indicates the truth of the expression against that variable. So for some variable, or for every type of variable which are denoted by existential and universal respectively, we denote an expression and assign it to be true for those variables. For example, it will be clear when I discuss the each of the quantifiers now. We have the universal quantifier which is for all, and this is a symbol here for universal quantifier, and this expression is true for every possible value of the variable. So when we write it like for all x, we have some statement s which is based on x. So this statement implies that for all x the statement s is true. Similarly, we have the existential quantifier there exists, or for some x. So this is the symbol right here for there exists, and this expression is true for at least one value of the variable, that is for at least one x the statement s is true, denoted by is for some x the statement sx. This denotes that the statement s is true for some x. First order logic in artificial intelligence. In the topic of propositional logic, we have seen that how to represent statements using propositional logic. But unfortunately, in propositional logic, we can only represent the facts which are either true or false. Propositional logic or PL is not sufficient to represent the complex statements or natural language statements. The propositional logic has very limited expressive power. Consider the following sentence which we cannot represent using propositional logic. Some humans are intelligent, or Sachin likes cricket. So in these two sentences, we are referring to first order logic and not propositional logic. To represent the above statement, PL logic is not sufficient, so we require some more powerful logic such as first order logic. Parts of first order logic. As a natural language, first order logic has two main parts. Just like natural languages, it has two parts which are syntax and semantics. The syntax of first order logic determines which collections of symbols is a logical expression in first order logic, and the basic syntactic elements of first order logic are symbols. We write statement in shorthand notation in first order logic. Now we see more details about atomic sentences. Atomic sentences are the most basic sentences of first order logic. These sentences are formed from a predicate symbol followed by a parenthesis within a sequence of terms. We can represent atomic sentence as predicate and bracket open term 1, comma term 2, comma and so on up to term n bracket close. Examples are Ravi and Ajay are brothers are indicated by brothers in brackets Ravi and Ajay, and Chinky is a cat is represented by cat in brackets Chinky. So these two Ravi and Ajay are terms here, and brothers is the predicate here, and here cat is the predicate and Chinky is the term for that predicate. Similarly, as we have seen, complex sentences are made by combining atomic sentences using any of the connectives which we have discussed earlier. First order logic, subject and predicate. First order logic statements can be divided into two parts. First one is the subject, which is the main part of the statement, and predicate, which can be defined as a relation which binds two atoms together in a statement. For example, we have seen the brother predicate, which binds two brothers or two terms, Ajay and Vivek, together. Consider the statement x is an integer. It consists of two parts. The first part, x, is the subject of the statement, and second part is an integer, is known as a predicate. So here we have a statement x is an integer. In this, x is the subject because it is the main part of the statement, and predicate is an integer because it is a relation which is specifying about the subject x. Now we'll see again a little bit more about quantifiers in detail. So a quantifier is language element in first order logic which generates quantification, and quantification specifies the quantity of specimen in the universe of discourse. So quantity can be for all or for some from the existential quantifiers for all and for some x that we have discussed earlier. These are the symbols that permit to determine or identify the range and scope of the variable in the logical expression. So quantifiers are the symbols that determine the range and scope of the variables in the logical expression that follows them. So the range can be again for all or for some as discussed earlier. There are two types of quantifiers. Universal quantifier, which is for all, everyone and everything, or existential quantifier, for some, at least one. Universal quantifier. Universal quantifier is a symbol of logical representation which specifies that the statement within its range is true for everything or every instance of a particular thing. The universal quantifier is represented by a symbol for all as shown here, and which resembles an inverted A. If x is a variable, then for all x is read as for all x, for each x, and for every x. So for example, we have this predicate here: x1 is intelligent, and x2 is intelligent, and x3 is intelligent, and so on till xn is intelligent. So this is the universe of discourse, and all elements of this universe are boys, and they are all known to be intelligent. So we can write as, in shorthand notation, we can write it as: for all x, boys x implies intelligent x. So for all x which are boys, it is known that x is intelligent. It will be read as: there are all x where x is a boy who is intelligent. Or in other terms, for all x, x is intelligent who is a boy. Existential quantifier. Existential quantifiers are the types of quantifiers which express that the statement within its scope is true for at least one instance of something. It is denoted by the logical operator as shown here, which resembles an inverted E. When it is used with a predicate variable, then it is called as an existential quantifier. If x is a variable, then the existential quantifier will be for some x, or for some in bracket x, and it will be read as: there exists a x, or for some x, or for at least one x. So we will discuss an example of existential quantifier now. So for example, we have this statement: some men drink coffee, and we have a set of predicates from here to here to represent that. Here we have the universe of discourse as the set of people or set of men x1, x2, x3, x4, x5 up to xn. And the first statement says x1 drinks coffee. The second statement is x2 drinks tea, and then x3 drinks milk, and so on, and xn drinks milk. So here these all are known to be true statements, that since they are connected by an AND operator here. So in shorthand we can write it as: for some x where x is a man, x drinks coffee. So it will be read as: there are some x where x is a man who drinks coffee. Now some properties of quantifiers. In universal quantifier, for all x, for all y is similar to for all y and for all x. In existential quantifier, for some x and for some y is similar to for some y and for some x, but when they are merged together, that is universal with existential, for some x for all y is not similar to for all y and for some x. Free and bound variables. The quantifiers interact with variables which appear in a suitable way. There are two types of variables in first order logic which are given below. A free variable. So what is a free variable? It is a variable in a formula which occurs outside the scope of the quantifier. For example, we have this first order logic statement here: for all x and for some y, there is a predicate p which is known to be true for the terms x, y and z. So here, since z does not have a quantifier on it, it will be a free variable. Similarly, in contrast, we have the bound variable. A variable is said to be a bound variable in a formula if it occurs within the scope of the quantifier. For example, in this example, for all x, the predicate ax and by, x is the bound variable. Now we move on to the concept of reasoning in artificial intelligence. The reasoning is the mental process of deriving logical conclusion and making predictions from available knowledge, facts and beliefs. As we have discussed in part 1, it is a type of inferencing or reasoning are the same terms, and we can say Reasoning is a way to infer facts from existing data. So when we have a knowledge base and we infer new logic from it, it is known as reasoning, as discussed earlier as well. So it is a general process of thinking rationally to find valid conclusions. Now we study a very important topic, types of reasoning. In artificial intelligence, reasoning can be divided into the following categories. First one is deductive reasoning, next inductive reasoning, next abductive reasoning, next common sense reasoning, another one is monotonic reasoning, and finally non-monotonic reasoning. We will discuss each of them in detail now. What is deductive reasoning? Deductive reasoning is deducing new information from logically related known information. It is a form of valid reasoning, which means the argument's conclusion must be true when the premises are true. So deductive reasoning is a type of propositional logic in AI, and it requires various rules and facts. It is sometimes referred to as top-down reasoning and contradictory to inductive reasoning. In deductive reasoning, the truth of the premises guarantees the truth of the conclusion. So it is a top-down reasoning in which we are given facts and we have to derive the truths or new logic from the facts. So it is contradictory to inductive reasoning. We will discuss inductive reasoning later. So deductive reasoning mostly starts from the general premises to the specific conclusion, which can be explained by below example. The example is, the first premise is all the humans eat veggies. The second premise is Suresh is human. So we derive the conclusion Suresh eats veggies from these two statements. So this is deductive reasoning since the conclusion is based on facts, and these are the facts here, and this is the conclusion which is derived from these facts. So it is a top-down approach as seen here. So the general process of deductive reasoning is given below. Process I mean. Uh, First we have the theory, next we form the hypothesis, next we have the patterns, and finally we get the conclusion or confirmation. So these are functionality of the particular inference engine. These are the facts and this is the conclusion. Next we discuss inductive reasoning. Inductive reasoning is a form of reasoning to arrive at a conclusion using limited sets of facts by the process of generalization. It starts with a series of specific facts or data and reaches to a general statement or conclusion. Inductive reasoning is a type of propositional logic which is also known as cause-effect reasoning or bottom-up reasoning. So, inductive reasoning is bottom-up and it is a cause and effect reasoning. In inductive reasoning, we use historical data or various premises to generate a generic rule for which premises support the conclusion. What is meant by this statement is, in inductive reasoning, we use the data within the premises to generate a rule, and that rule is supported by all the premises to arrive at the conclusion. In inductive reasoning, premises provide probable support to the conclusion. So the truth of the premises does not guarantee the truth of the conclusion. So this is probable support, which means only a basic probability of truth is provided to the conclusion by the premises. So if the premises is true, it does not guarantee that the conclusion is true. For example, we have the premise all of the pigeons we have seen in the zoo are white, and the conclusion is therefore we can expect all the pigeons to be white. So this statement here is not true, but the premise is true. So the premises do not guarantee the conclusion. That is inductive reasoning. So similarly, we have the process here. We have the observation first. Next we see patterns. So next we form the hypothesis out of those patterns, and we form a theory that may or may not be true based on the hypothesis. So this is inductive reasoning. Next we see what is abductive reasoning. Abductive reasoning is a form of logical reasoning which starts with single or multiple observations, then seeks to find the most likely explanation or conclusion for the observation. Abductive reasoning is an extension of deductive reasoning, but in abductive reasoning, the premises do not guarantee the conclusion. So, for example, we have the implication or premise: cricket ground is wet if it is raining. The axiom is cricket ground is wet. Conclusion is it is raining. So here the implication is cricket ground is wet if it is raining, and it is known that the cricket ground is wet. So we derive at the conclusion it is raining. But the conclusion is may not be true based on these two statements. And so this is a part of deductive reasoning, but uh, in this the conclusion may or may not be true. Next we see common sense reasoning. Common sense reasoning is an informal form of reasoning which can be gained through experiences. Common sense reasoning simulates the human ability to make presumptions about events which occurs on every day. It relies on good judgment rather than exact logic and operates on heuristic knowledge and heuristic rules. So, common sense reasoning relies on judgment rather than logic, and it operates on heuristic knowledge and rules. For example, one person can be at one place at a time. This is common sense. If I put my hand in fire, then it will burn. This is also common sense. The above two statements are the examples of common sense reasoning, which a human mind can easily understand and assume. Next, we move on to monotonic reasoning. In monotonic reasoning, once the conclusion is taken, then it will remain the same even if we add some other information to existing information in our knowledge base. So suppose we have a knowledge base and we take a conclusion out of it, then that conclusion will remain the same even if we add more knowledge to that knowledge base. So in monotonic reasoning, adding knowledge does not decrease the set of propositions that can be derived. That means if we add knowledge, then also all the propositions that can be derived from the knowledge base will remain the same, and the conclusion will not change when we add knowledge. So to solve monotonic problems, we can derive the valid conclusion from the available facts only, and it will not be affected by new facts. So, so when we have a monotonic problem, we can derive the valid conclusion from the available facts only, and that fact will not be affected by new facts. And monotonic reasoning is not useful for the real-time systems, as in real-time facts get changed. So we cannot use monotonic reasoning. Monotonic reasoning is used in conventional reasoning system, and a logic-based system is monotonic. Any theorem proving is an example of monotonic reasoning. So is in maths and mathematics, you must be have seen that we have a set of theorems and we derive one theorem from a set of other theorems. So this example is a set of monotonic problems solving, and example will be earth revolves around the sun. It is a true fact and it cannot be changed even if we add another sentence in the knowledge base like the moon revolves around the earth or the earth is not round, etc. Next we have the non-monotonic reasoning. In non-monotonic reasoning, some conclusion may be invalidated if we add some more information to our knowledge base. It is in contrast to monotonic reasoning, in fact. So logic will be said as non-monotonic if some conclusions can be invalidated by adding more knowledge into our knowledge base. Non-monotonic reasoning deals with incomplete and uncertain models. Human perceptions for various things in daily life is a general example of non-monotonic reasoning. Example, let's suppose the knowledge base contains the following knowledge. Birds can fly, penguins cannot fly, and Pity is a bird. So from the above sentences we can conclude that Pity can fly. However, if we add one another sentence into knowledge base like Pity is a penguin, which concludes Pity cannot fly, so it invalidates the above conclusion.